Hello again, everyone. Thank you for staying with us in this series. So today, well, previously, we talked about thin lens terminology, and we also analyzed the image of an object outside the focal point. So please check those out if you need a refresher. Today, we're going to do the same, but with the object being inside the focal point, okay? And a very good application for this is a magnifying lens, a magnifying glass. If you have a magnifying glass, you can practice and see this. Basically, put the magnifying lens over a book or a piece of paper and move it out. And as you move it out, basically your object is inside the focal point of that lens, okay? And you move it out and you move it out. As you move it out, eventually everything will go white or blurry. You can't see anything. That's when the object is at the focal point. And then you move it out some more, the letters and everything will flip. And that's what we did in this video right here, second video. You saw the image was inverted from the object, okay? And maybe we'll do a little lab with this one, and we'll also do some problems. Right now, let's analyze this image of the object located inside the focal point. So again, before we begin, please like, subscribe, and share this on your social media and provide us with comments in the comment section. All right. So again, we're going to start with the ray tracing. Here is the focal length. It's still a focal point. We still have f as 6 units, but now we have the object distance at 4 units, and the object height is 2 units. Right? And let's see where the image will land here. So just like before, we have 3 principal rays. The first ray is coming parallel to the optical axis, exits the lens through the focal point. So let's get one going parallel to the optical axis. And then exits the lens going through the focal point. So here's the focal point right here. Let's see if we can get it through by hand. There it is. Roughly. There we go. Maybe I can do better with one more. There you go. All right. The second one, ray going through the center of the lens, exits undeflected. Okay, so let's take it a green. Here is the center of the lens. So let's draw one from the tip. It's going to go through the center undeflected. And then the third one is going to be just like before. Through the focal point, exits parallel to the optical axis. Well, we cannot get a ray through that focal point right here, right? It has to go through the focal point. Usually it's on this side. So if we have a ray coming in like this, it's going to go down this way. What we can do is we can say, okay, let's have a ray coming in, appearing as if it's coming from the focal point, and then it hits the mirror or the lens up here somewhere. There you go. So this ray appears as if it's coming from the focal point, and then it goes out parallel. Okay. So in the previous video, we had all the rays meet on the right side of the lens. They all intersected at one point, and we said, okay, that's the tip. That's the tip of the arrow, and the tail of it is on the optical axis, and we're able to draw the arrow. But right now, if we look on the right-hand side, there is no way the orange, blue, and green lines are going to meet on that side. So in this case, what we do is we trace back those rays, okay? We trace them back. And then let's trace the green one back. And they meet at this point right here, okay, when we trace them back. So if somebody is looking from over here, they will see light coming in from the tip. So we see basically the tip of the arrow over here, and then the tail is over here, okay? Obviously, they will not see the object. They'll see the image, and they'll see an image or something emitting light from over here. There it is. That's what they'll see, basically. And what we're going to do is we're going to draw a dashed line, because light does not actually converge at this point, or at, for this arrow. Light appears to be coming from this arrow. So this is called a virtual image. So this is a virtual image. And this is its distance, d sub I. This is its h sub I. So what is d sub I? Let's see. This is 6, 7, 8, 9, 10, 11, 12, 13. So I got here d sub I to be negative 13 units. Negative, again, going back to the first video on thin lens terminology, it is on the same side as the object. It is basically a virtual image. Light does not come from it. It appears to be coming from it, okay? In the previous problem, when the object was outside the focal point, light actually converged at the image. The image was real, okay? Here, it appears to be coming from that. It is virtual and it's upright. So we can also add some here. It's upright right there. And it's 1, 2, 3, 4, 5, 6, 7 units high. So h sub O is plus 7. Okay. And again, this is a rough estimate, just doing it by hand. Okay. So let's see if you do it using a ruler. That's what I got. Rays are much better. Okay. So let's see now. If you do a rough drawing by hand, how far are you? Let's see, 6, 7, 8, 9, 10, 11, 12. So I was off by 1 unit. Let's see here. We got 13, right? 6, 7, 8, 9, 10, 11, 12, 13. So I was off by 1 unit. And then the height is 1, 2, 3, 4, 5, 6. So this is obviously a much better image. But this doesn't mean this is wrong, okay? Usually what you do in these problems, and as we will do in whenever we work out some exercises, this will give you an idea what the image is going to look like. The thin lens equation will give you exactly where the image is located and magnification and all. This is just an idea. You draw a couple of rays, 3 rays, you see, okay, my image is going to be virtual, it's going to be upright, and it's going to be larger, roughly 2-3 times as large as the object. Now you go and you do your actual computation using the thin lens equation to verify that. So here actually what we got, the DO is 4 units, F is 6 units, HO is 2 units, HI is 1, 2, 3, 4, 5, 6 units. And DI is negative 12 units. Now we know everything about the image. It's upright and it's virtual. And it's 6, so it's 3 times. So basically, HO is 3 HI. Okay? 3 times as large as the other one. Let's see if now the lens equation matches this. Again, this is a precise drawing, and sometimes you may want to do ray tracing precisely, okay? But again, most of the time, you do ray tracing as a rough, give you a rough idea where the image should be, and then you go and verify it using the lens equation. So let's do the thin lens equation. So again, 1 over F is 1 over DO plus 1 over DI. And just like last video, I'm solving for DI. So I bring DO over to this side. And when I do so, I change the sign on it. Here I combine these two by cross multiplying. So I'll have DO minus F over F times DO equals 1 over DI. I have one single, one fraction on the left, one fraction on the right. I can flip both. F times DO over DO minus F is 1 over DI. Now DI, I guess I can take it to the other side right here. DI is, no, I didn't flip this, did I? This is supposed to be DI right here. Now just put DI, flip the equation so it can look better. F times DO, the DO minus F. And again, F was 6 units. DO was 4 units. So DI, F is 6 times 4 over 4 minus 6. 24 over negative 2. And I'm going to get a negative 12 units. So right away, this tells me that we have a virtual image. It's on the same side as the object. And again, please go check the introductory video on thin lens terminology. And again, this is verified by this. They both sort of complement each other. If you do an exact ray tracing, we got 12 on the same size of the object, and it's virtual, which means whenever we do the magnification, it's going to show that it's upright, and then it's 3 times as large. All right, so let's do now the magnification. Magnification is negative DI over DO, or negative 12 over DO is 4. Negatives, 2 negatives me a positive. 12 over 4 gives me 3, which is what I expected. Okay, again, M is positive. That means image is upright. Now, how large is that image in terms of units? So M is also by definition HI over HO. So HI is M times HO. 3 times HO was 2 units. Let's put a times here if you want to. 6 units. Again, it's 6 units, which we counted 6. Positive meaning is pointing up. So now we have the image, summary, virtual, upright, 6 units, and then 12 units to the left of the lens. Okay, we don't need to put negative here, right? If we just say negative 12 units, then we leave it up to the reader to know that is to the left of the lens. Or we could say it's 12 units to the left of the lens. Again, the negative and left of the lens mean the same thing. Okay? And this is it. We know everything about the image right now. Okay? And just by ray tracing and thin lens equation. And again, in complicated systems, in multiple multi-lens systems, compound lens systems, ray tracing becomes a software issue. Okay, there are specialized software to do that. Usually you use lens equation. You do one lens at a time using the lens equation to find what the final object is. Okay, ray tracing becomes cumbersome after you have 3 or 4 lenses. Okay, and this is all. This is all we have. So next, we'll try to do one set of exercises. Maybe we'll do 2 separate videos. So thank you for joining us, and I hope to see you in the exercises and solutions video. Thanks again.